Okay, guys, here we go again. This time, like I said, I've been talking about trying to do chapter 4, some of those problems for a while now, and I ended up getting caught doing some lectures I wanted to do. Sooner or later, it's all got to get done. So I figured the lectures on the front end of it, if I get those out of the way, I think it's better for you guys if you have some of that machinery, as they say, right in front of you. So let's figure this out. So let's knock out these problems, guys. What I got all right, guys, chapter 4. And let's see what we have here. So for chapter 4, I'm going to try to go comprehensively, relatively fast. I think we got a lot of the machinery, as they say, under control, because we've talked a lot before we've even attempted to do some of this stuff. So I think we're going to be okay. So here we go. Problem number 16 from chapter 4. 16 from chapter 4. If the vector components of the position of a particle moving in the xy plane as a function of time are x bar equals 2.5 meters per second t squared I vector, and y vector is 5.0 meters per second cubed t cubed j vector, at what time t is the angle between the particle's velocity and the x-axis equal to, at what time t is the angle between the particle's velocity and the x-axis equal to 45 degrees. Okay, so it's a kind of a somewhat odd problem, the way it gets asked, but I think the best way to say this is if you can somehow look at this, we can figure out where we're going to go. So I think what we could say here is, I'm not crazy about how I actually went about trying to talk about it. Okay, yeah, actually, it's not bad. This is not a bad way to look at it. Let me stay with where I'm at. Basically, guys, this is kind of a tough one. I mean, it's a little tough to visualize in some regards. You are basically saying that the y component and the x component are equal in magnitude. I think where you got to go with this when you try to say something like this. It's kind of odd the way they say it. You know, if the vector components of the position of a particle moving in the xy plane as a function of time are as they gave it, so they gave, there's a lot here, so let's talk before we go there even. They gave us x bar is 2.5 meters per second. Now these are going to work out in such a way that we're going to get the right answer. So that's not, it's meters per second squared or meters per second cubed. Let's bypass the units if you allow me to do so. But you got to be extremely careful when you're bypassing units. All the units are going to come out just right. These are vector quantities, so the direction is going to be different. But in terms of the units moving in a particular direction, the units are going to be the same at the end of the day when we're doing something like this. So we got this. All right, it's looking good, So what they're saying here, at what time t is the angle between the particle's velocity and the x-axis equal to this? That's interesting. Basically what they're trying to say is, if it's going to be a 45-degree angle, this thing's got to be making a 45-degree angle. The component's got to be making a 45-degree angle in regard to velocity. So if it's given like this, we got to be extremely careful, I guess you could say. This is position, whereas velocity is going to be dx dt. It's going to be dy dt, depending what you're talking about. So you got to be kind of really cautious of what's going on here. I've got to compare the two velocities, Vy and Vx, and they got to be essentially they got to be equal magnitude, because if they're both equal magnitude, then there is an angle being made of 45. They're both positive, both equal magnitude. We're not going to split too many hairs on this. There's going to be a 45-degree angle if Vy and Vx are going to be equal. It forms the isosceles right triangle, and that gets us there. That's the real big thing here. Well, if we're going to play that game, you guys, take the time derivative here, first time derivative here, and you get, right? You get that, and you get the other one. And again, strictly speaking, these are vectors. Then you got the other one, dy dt, and let's do it. Take the time derivative. And we got it. The tan of theta, do what I wrote. Do what I wrote. Which is get that right there. So tan let's see what we got. We got this. Do the division. It's looking like that. Did something just happen here? Yes. Something happened. I shouldn't. This is what I wrote here is true, but it's not the entirety of the truth of what I want to be doing here. Let's talk some more. We're talking about a 45-degree angle here, guys. The tangent of a 45-degree angle T is kind of a weird thing. I think there's a number of ways this can go. I think I'm splitting too many hairs here. Just to be safe, let's see what I can say. First of all, 0 is not acceptable. 0 divided by 0 is not defined. So 0 is going to end up being a solution, but it's not going to be an acceptable solution. 1 will be, though. 1 here times 5 is 5. 1 squared times 15 is 15. 15 divided by 5. Actually, no, I take that back. 1 will not be either. Let's figure out what it is. Let's multiply by 5t on each side. Let's solve this, but let's solve it carefully. T equals 0 works mathematically, so to speak. T equals 1/3 seconds also works, and it really works. Zero ain't working, guys. It's not going to work. I can't really go 0. If I do, I got 0 divided by 0, and I'm claiming it's 1. That's really not valid. This does work. T equals 1/3 does work. T equals 0.333 seconds will be what we need. Okay? That's 16. Let's go to the next one, 19. Okay, guys. Keep going here. Okay, just want to check that you can hear me okay. Let us continue. For 19. 19 is saying the spiral is an example of a mathematical form appearing in nature from the visible construction of seashells, pine cones, and galaxies to the movement behavior of certain animals. The position of a hungry animal that moves outward along a spiral path searching for food can be written as, and we have something written there. Write an expression for the velocity of the animal in component form. Okay, should be pretty straightforward. Again, caution is required on this, as always when we're doing these problems. So let's have a look. Let's see what we got here. So they're giving us this. And that's, it's pretty, very impressive equation, I can say. And there's a lot you can do here. I mean, is there an easy way? Is there a hard way? I don't know. I do know that this is occurring in both places in the sum, so why not just take it out? Why not just do reverse distribution of that whole thing? Do reverse distribution of that whole thing. And it's called factorization, right? And obviously, so we got this. So we're looking pretty good. Look at something like that. If you want to do this, if we do what they're asking us to do, we need to, again, we need caution on this. It shouldn't be too bad. All right, let's see what we can say here. Way I want to look at it is this, guys. I'm going to call this big thing right here. I'm going to call that a function. That's a function, and this is another function. This is f. This function is f. This function is g. The derivative of the product f times g is f prime g plus g prime f. By the product rule, the derivative of the product of f and g is f prime g and plus f g prime. So that's basically what you're doing here. Well, let's get the derivative with respect to time of a omega t. That's just a omega. And that comes out to here. A omega, and then you got the whole song and dance that We got that. And the other one is leave it alone and get the derivative of the other guy. And that's that's its own little mess, I guess, right? But you get the derivative of this guy, and that's negative sine omega t times omega. So that's negative omega sine omega t for that one, I. And the other one is omega cosine omega t. Times j. And that's it. And what's going on here? Is there a way we can kind of look at this thing and make a little bit of sense out of it? I mean, there's a lot here. Let me just see where I stopped, and I think there's probably a number of ways you can go here, but probably there's so many ways you can look at this, I guess, apparently. But yeah, I think, let me just think here. I want to make sure I did this the way that they want to see this done. Okay, I think the way we did it, we got to that. They got a t there. You can bring a t here. And for some reason, I'm just trying not to, I'm having a hard time believing some of this stuff that's here. This right here, you can bring the t inside, and I think what we're going to get is, yeah, I think I'm probably writing the exact same thing that I have written down. For some reason, I'm not believing some of my own writing here. Let's have a look here. I think I see what they've done. That plus sine omega t j plus omega, let me see what the heck, negative omega t sine omega t. I'll just bring the t inside on both of these. There it is. Just trying to, yeah, right. It's essentially the same exact thing that I wrote. Let me just see here. Cosine omega t minus sine omega t. No, it's not. I don't know. It's kind of a horse apiece on these. You guys, how I'm actually doing this. This should absolutely be fine. For some reason, okay, I see what happened. To make it a little easier to look at, you put the eyes together, and you put the J's together. And when you do that, okay, that explains everything. Here it is. You've got basically so here are the I's. So it's cosine omega t plus a negative omega t sine omega t. We got that. That's I. Then we got the other. Okay, that was kind of the logic here. And the other one is sine omega t. Sine omega t plus omega t cosine omega t. Just saying it and writing it's harder than actually doing it, you guys. But that's about where it went. A omega times the quantity cosine omega t plus negative omega t sine omega t plus A omega times the quantity sine omega t plus omega t cosine omega t. This is an I component, that's a J component, and you are done. At the end of the day, it's coming out right there. At the end of the day, it's coming out right there. So that's that. Let's go to 20. For 20, they're saying a circus performer stands on a platform and throws an apple from a height of 45 meters above the ground with an initial velocity v0 vector. A second blindfolded performer must catch the apple. If v0 is 26 meters per second, how far from the end of the platform should the performer stand with all that is going on right there? Okay, so all right, guys, 20. It's a fascinating question in its own right, you know. It's a pretty neat question. We're not worried about, I mean, they already kind of accounted for a lot of stuff going on here, guys. Person standing. There's the person. Does not look like a person, but okay, we'll just say I can't. But then again, what I draw is not that good either normally. So, but you got something looking like this. That's V0. That's a 25-degree angle right there. It's 45 meters height. How far does the person got to be standing, you know, from where this is all happening? So we're saying from here out to here. We're not really concerning ourselves with how tall the person is who's catching. Something like this. How far away does he have to be standing for this thing to work out? We'll take it from there. What happens is, guys, we got a lot of stuff that has to happen, I guess you could say. We have to find out, there's got to be a component this way, and there's a downward component. Component this way is V0 cosine 25 degrees. So that's true, but at the same time, this thing's got to fall down. The initial jolt, I guess you could say, V0 sine 25 degrees going down. Let's go. It's going to cover a distance x to get caught. It's going to cover a distance x to get caught, and there's V0y t plus 1/2 gt squared. Remember now, they're going down. It's falling down. This is 45. This is V0 sine 25 degrees. This is a half. You got this. So what we got here is we got this. We've got this. there are distances involved and a whole lot of other stuff. We're trying to find out what the distance involved would be. We're told it gets fired at 26 meters per second. V0 is 26 meters per second. So what you're going to have is you've got this and you've got this. So let's see what we got. I mean, at the end of the day, those two are going to run the show, how we're going to do this. Let's find out how much time you got. I mean, how much time you got is going to determine how far it's going to go. It's as simple as this. The distance here is this. Forgive me. It should have been time as well, right there. Should have been time as well. So x equals V0 cosine 25 degrees t, and this right here. Let's find out the time. Here's 45. V0 is 26. The sine of 25 is what it is. Half of 9.8 is 4.9 plus that. Let me plug in all those numbers and see what I got. Then I got 45. Let me rewrite that. We got that. T is equal to, plug this into the quadratic equation, you guys. The quadratic equation, the opposite of b plus or minus the square root of b squared minus 4ac the whole thing over 2a. What you end up getting is t equals 2.11 seconds. T equals negative 4.35 seconds. Negative time's not for us. It ain't working. I mean, for the physics we're doing, we're leaving it like this. T equals 2.11 seconds. 2.11 seconds is going to get plugged in for t. This is 26. This is 26 meters per second. This is the cosine of 25 degrees. And this is 2.11 seconds. Plug in all those numbers. (26) cosine 26 times the cosine of 25 degrees times 2.11 seconds. 49. For this to work, you got to be 49.72 meters away from the person when they're launching this thing. When they're firing it down at us. 49.72 meters. Uh, 30. A projectile is launched up and to the right over flat level ground. If air resistance is ignored, its maximum range occurs when the angle between its initial velocity and the ground is 45 degrees. I've already talked about that in another video. What angles could result in the range being equal to half the maximum? That's interesting. All right, let's take a look at it. We know that when the maximum is going to occur at a 45-degree angle of firing. At a 45-degree angle of firing, the maximum occurs. Great. What two angles would give me half the maximum range? The maximum range at 45 degrees. What two angles would give me half the maximum range? Interesting. So, how you doing? Well, tell you what, we know that the range, R, it's also X, right? They call it X. I'll call it R right now. Is V0 squared over G sine 2 theta, depending what theta you're talking about. R max divided by 2 is going to be V0 squared over G sine something, I guess, sine 2 theta, sine 2 phi, sine something. We know that R max occurs when the sine function is equal to 1. That happens at a 45-degree angle. 2 times 45 is 90. 2 times 45 is 90. The sine of 90 degrees is 1. So R max is going to occur right here. Okay, believable. So I'll tell you what. Let's figure out how it's going to be half. R max divided by 2 is half the maximum range. Divided by the maximum range, that ratio is going to be a half. And that's V0 squared over G sine 2 theta over V0 squared over G. Okay. R max and R max cancel. You've got a half. V0 squared over G. V0 squared over G. Cancel. You got sine 2 theta. The aforementioned fractional values to the following, we're talking about this. Let's talk. Let me get the inverse sine of sine 2 theta, and let me get the inverse sine of a half. The inverse sine of the sine function is just the original thing that was in the argument, 2 theta. The inverse sine of a half is 30 degrees. Theta is a 15-degree angle, is going to give you half the range. Yeah, I got another one, though, for you, too. We know that. We know the sine function is a pretty fascinating function. I mean, here's part of it. This gets you all the way to pi. This is pi over 2. This is 90 degrees. If 15 is where this happens, 15 away from this place is where that happens. 15 away from this place is where the same thing happens. This is 85. This is 15. Because of the symmetry, this is a horrible drawing on my part, guys, but I think if you can just use your imagination a bit, use a lot of imagination, I guess, but I mean, the way it goes, you see the way that it goes, guys. If it's 75 away from 90 and 75 away over here, well, 75 here, that's not, forgive me. See exactly how we want to talk about this now, guys. You'd want, for this thing right here, if 15 away from here and 15 away from here is 165. Now I got it. Now we got to be careful. Let me stop. Let me stop for 1 second, guys. Trying to think about this. Should have thought. I have the right idea, but I'm going in the wrong direction. So, make a long story short, I wasn't doing it right. If I go here, let's try it again. At a 30, I know it's 15 right here, but at a 30-degree angle, this is the top for the sine function, 90 degrees. At a 30-degree angle, you got half. 30 degrees this way. 30 degrees from there. 30 degrees from here, you also got half. This is 150 degrees. Half of 30 is 15. Half 150 is 75 degrees. These are the two answers. The symmetry of the sine function dictates that 150 and 30 work. Well, how'd you get 30? I doubled 15. How did you get 150? I doubled 75. So you gotta be careful. You gotta be careful. But that's where we're going. That's where we're going. You got theta is this, and you got either one of those, you guys, is going to give you the same range. One is going to give you a lot of flight time, so it doesn't have to be going that fast horizontal. This will give you a lot of flight time, so you don't need a great deal of horizontal velocity to get the job done. This one won't give you a lot of flight time, but man, it's just firing straight out at it. So that's kind of neat too. So that's it. That's 30. Let's go to 38. All right, guys, for 38, two particles A and B. Two particles A and B move at a constant speed in circular paths at the same angular speed omega. Particle A's circle has a radius that is twice the length. Particle A's circle has a radius that is twice the length of particle B's circle. What is the ratio, T sub A over T sub B, of their periods? Okay, neat question. So let's see what we got. So for 38, just remember, guys, if you got an omega, you're going to cover 2 pi radians in the period of time. Remember, the omega is the total number of radians in a circle divided by the period. 2 pi equals omega t. We were told that omega A equals omega B, and we'll just say equals omega. Omega equals omega A equals omega B. They're equal in that regard. So let us see what is going on here. If the omegas are equal, it's a lot easier than you think it is. Basically, man, this kind of solves the problem, is what it does, guys. T sub A, what's T equal to? 2 pi divided by omega. So T sub A, what would T equal? T would equal 2 pi divided by omega. 2 pi divided by omega sub A. T sub B would equal 2 pi divided by omega sub B. Man, didn't we just say that omega sub A and omega sub B are equal? T sub A equals 2 pi over omega sub A equals 2 pi over omega equals, well, the same thing as saying this, 2 pi over omega sub B. They're all equal, but that right there is equal to T sub B. This guy and this guy are equal. The periods are equal. I'm trying to throw you off. Divide by T sub B on each side. T sub A divided by T sub B. T sub A divided by T sub B is equal to 1. Here we go. $39. For particles A and B in the above problem, you guys, what is the ratio V sub A over V sub B of their translational speeds? That's a different story. That's a different story. Let's kind of stay with that. What's going on here? Now we already said the omegas are all equal. V sub A over V sub B is omega A times R times RA. Omega sub B times R sub B. We already said that omega A equals omega B equals omega. Omega A and omega B are equal. They cancel. So, at the end of the day, VA over VB equals RA over RB. They also told us that RA has a diameter. Look, did they say diameter, radius doesn't really matter? Let me just be sure. Doesn't matter though. Has a radius. Okay, that's fine. So, particle A's radius has particle A's circle has a radius that is twice the length of particle B's circle. Particle A's radius has a radius that is twice the radius of particle B's radius. Particle A's circle has a radius that is twice the radius of particle B's circle's radius. RA equals that. So that's all it is. That's all it is. So what happens is this is 2RB. This is RB. 2 to 1. That's it. I mean, there's various ways you can do it. So let me write that here, guys, and I'll eventually erase all this. For 39, VA over VB VA over VB is 2 to 1. Okay? All right. 40 for particles A and B in problem 38 again. What is the ratio of the accelerations? A sub A over A sub B of their magnitude of the magnitude for their centripetal accelerations. Okay, we'll talk about that. That should be pretty straightforward as well, you guys. So how do you want to do this one? Well, didn't we say omega's the same now, guys? Omega's the same on all these, and that's going to play a big role. Let's do a ratio of those two. That's omega sub A squared RA. This is omega sub B squared RB. Here we go again. Omega sub A is omega. Omega sub B is omega. Same thing. RA is 2RB, and RB is just RB. That's out of there. 1 to 1 ratio. 1-to-1 ratio here. And there it is. AA over AB two to 1. $49, $60, $68, $70. Let's run through it. What's 49 saying? Number 49. Be very careful how you answer these questions, guys. Be very, very careful how these questions get answered. Okay. For 49. A man paddles a canoe in a long, straight section of a river. The canoe moves downstream with a constant speed of 3 meters per second relative to the water. The river has a steady current of 1 meter per second relative to the bank. The man's hat falls into the river. 5 minutes later, he notices that his hat is missing and immediately turns the canoe around, paddling upriver with the same constant speed relative to the water. How long does it take the man to row back upriver to reclaim his hat? Okay, so a rather interesting point going on here, guys. The man's in the water, and let me just see here, guys. I'm looking at this a little differently than what I had planned to do, but okay. So a man paddles a canoe in a long, straight section of a river. Give me 1 second here. I'm going to just look at one thing here. I'm going to straighten something out. All right, everybody. Forgive me the pause there. I wanted to write some stuff on the board, kind of look at it. I was sort of looking at this thing cold. The guy discovered, let's say, that he lost the hat 5 minutes ago. I mean, it's as simple as that. He was going down the river. Everything's going okay. He's going down the river, and at some point, he discovered he lost his hat. It fell into the water. Now he's got to go get the hat. He's got to recover it. The hat didn't get ahead of him because the hat's not going faster than he's going. He's paddling 3 meters per second faster than what the water's going. So only the water is going to be carrying the hat. The water is going at 1 meter for problem number 49. The water by itself relative to the bank is going 1 meter per second. This person is going 3 meters per second relative to the water. So he's going 3 meters per second relative to the water, and the water is just going 1 meter per second relative to the bank. So once he lost his hat, the hat's going slower than he is because he's going 3 meters per second downstream. Plus, he's going 3 meters per second while he's going downstream relative to the water, 3 meters per second relative to the water, and the water itself that he's in is moving at 1 meter per second. So 1 meter per second and 3 meters per second is 4 meters per second as he's going downstream. So 5 minutes, the hat was lost. 5 minutes is 300 seconds. He's going 4 meters per second relative to the bank. Downstream, relative from tree A to tree B, he's going 4 meters per second. The water's going 1 meter per second, and he's in that water, traveling with the water, and he's going faster than the water itself relative to the water. He's going 3 meters per second in the water. Relative to any particle of water that's moving, Relative to that moving particle, he's going 3 meters per second faster than the water's moving. So 1 meter per second plus 3 meters per second is 4 meters per second. 4 meters per second times 300 seconds is 1,200 meters. 4 meters per second times 300 seconds, 4 meters per second times 300 seconds is 1,200 meters downstream in those 5 minutes. The hat that got into the water was going 1 meter per second in the water relative to the bank for 300 seconds. The hat's going 300 meters. The hat went 300 meters from where it fell in relative to the bank, whereas he went during that same amount of time from where the hat fell in. The hat went only 300 meters in that period of time of 5 minutes, but he went 1,200 meters, 4 times further than the hat because he was going 4 times faster than the hat. He's going 4 meters per second in total. If you add the 1 meter per second and the 3 meter per second, if you add the speed of the water and the speed of him relative to the water, 1 and 3 equals 4. He's going 4 meters per second. The hat just has the water to help it out along its path, and that's just 1 meter per second. So 4 meters per second times 300 seconds is 1,200 meters. 1 meter per second times 300 meters times 300 seconds is 300 meters. He is ahead of the hat by the difference of 1,200 and 300. He is 900 meters ahead of the hat. He is 900 meters away from his hat. He has to turn around and go 900 meters. Yeah, he's getting some help though. The hat is coming at him at 1 meter per second, and he's going upward at 3 meters per second, but the water's stopping him. So he's really just going 3 meters per second relative to the water minus 3 meters per second relative to the water minus the water fighting him back. So he's only going 2 meters per second upward, but the hat's coming at him at 1 meter per second. So grand total, that's 3 meters per second relative to one another. They're about to meet up. That's pretty fascinating stuff. What happens is, essentially, relative to one another, this is kind of a strange thing. Relative to one another, he's really beating the hat by 3 meters per second. Coming back, he's meeting up with the hat at 3 meters per second. So when you do all the math, you come back to 5 minutes. That's pretty interesting. Yeah, the hat's got help going down. Yeah, but he also has help going down that way. Relative to the hat, he's going 3 meters per second. Coming back, he's having to fight the water, but the water's helping the hat, so it compensates. So relative to one another, they are separating at 3 meters per second as he's losing the hat, and they are uniting relative to one another. So they're leaving one another, they're parting from one another at a relative speed of 3 meters per second as the gentleman's losing his hat. And that's 3 meters per second as the gentleman's losing his hat relative to one another. But as the gentleman comes back to regain his hat, they are meeting also at 3 meters per second, which means it's going to be the same amount of time. The amount of time it took him to lose the hat, so to speak, is the amount of time it's going to take him to gain the hat. Very interesting problem. Interesting problem. So, let's go to 60. Let me just see here, guys. For some reason, a couple of these I just hadn't done. I've done some other time, I think. That's all well and good, I guess. Let's see what we got. 60. 60. A golfer hits his approach shot. Let me see what we got. Yeah. A golfer hits his approach shot at a 50-degree angle, giving the ball an initial speed of 38.2 meters per second. The ball lands on the elevated green 5.5 meters above the initial position near the hole and stops immediately. A, how much time elapsed while the ball was in the air? How far did the ball travel horizontally before landing? C, what is the peak height reached by the ball? So there's a lot being said here, you guys. let's kind of take a look at it, I guess you could say. Let me think. So what's going on there? How did this whole thing proceed? Let's find out where we're going to go. So let's see exactly what we want to do in regard to this thing, how it all happened, how it's all going to play out. Okay, shouldn't be too bad. For some reason, guys, I'm having a hard time finding something here on the particular thing that I'm doing. But let me do this, and then we'll do this in a subsequent video. We'll probably hit 68 and 70. The next time we do this. I'd like to maybe take a little bit more time on 68 and 70. I'd probably like to take a little bit more time on 60, but let me at least do 60 right now and then come back to 68 and 70. So we got just a little more concentration on that. So like I said, I'll come back to 68 and 70 the next time I do a video on this thing for 68 and 70 from that one. For right now, let's look at 60, how that would approach. 50-degree angle. 38.2, let's use their language, I guess. 38.2 meters per second. This is not going to be a good drawing, guys, but let's at least try to make something right on this thing. There's the flag. There's where it hits. Thing's elevated. .5 meters. I mean, this is quite a bad drawing, guys. I'm sorry. I think you know where I'm trying to go, though. I mean, .5 meters. So what's going on here, guys? You got to find the time elapsed, the maximum height, and the range. You know, you got to find this right here. You know, what kind of range are we talking about? X. What kind of maximum height are we talking about? And how much time? Time ain't as bad as you think it is. What happens is you're going to find two times. One of them you're not going to take. The other one you are going to take. This thing has a height right here. If you go draw a horizontal line. Don't literally do it, but do it in your mind. Do it in your mind. Draw a horizontal line all the way across here. This is 5.5. At t equals 1 second, it's at 5.5. At t equals 100 seconds, it's also 5.5, let's say. So there's going to be two places it's going to happen. It's got quadratic equation written all over it, you guys. So what we can do is, on this, let me got an idea. Is it true that y equals VIY, or in this case, VOY t plus 1/2 gt squared? That's a negative g. That's a negative 9.8. So you can kind of just be careful what you call g. You want to call it negative, you want to call it positive. Make sure it's negative at the end of the day. If it's going up and down, it's got to be negative. Here we go. I want a height of 5.5. I want an initial velocity of 38.2 meters per second times the sine of 50 degrees times the time, plus 1/2 times negative 9.8, negative 4.9. That's what the time is, guys. That's what the time is. That's what the time's going to be. So you're looking at, the setup is going to be right about there. Okay, so let's come right back to here. This is going to give you the time. This is going to give you the time. And from there, you're going to, unfortunately, don't have a calculator on me right now, so I'll get back to it, but next time we get together, we'll do this. Let's get everything over to one side and see what happens here. This will give you the total flight time. Once you solve for t, you're going to have the total flight time. Then you're going to take v0 sub x, which is 38.2 times the cosine of 50 degrees. And then multiply by the t that you have, and that'll tell you the x. As far as the maximum height is concerned, you saw me do that. V0 squared sine 50 degrees over 2 times g. 2 times g is 2 times 9.8. And that'll give you the maximum height. Now, let me do that when we get back together again, guys. Let me leave this here. This stuff is useful enough that I think it bears a second look. But now that you see this on this video, you can do it before you even look at me doing it. Before you even look at me doing this, you'll be able to do it. Take a shot at it. I'll come back and do it. What are they saying here? They're saying how much time passed? How far did the ball travel horizontally? What is the peak height? You're going to solve this for t, and you're going to find the time. Go ahead and do it. Do the quadratic formula, grind this out, solve this for t. Solve this for t using the quadratic formula. And that's it. Solve this for t using the quadratic formula, and you'll have the time. Then you put that time times v0x times t. That time times v0x will give you the x displacement, horizontal displacement. 38.2 times the cosine of 50 degrees is the horizontal component of velocity times time. H is going to be v0 squared sine 50 degrees. V0, also this squared as well, forgive me. V0, V sub 0 squared, sine squared 50 degrees. Remember that. This guy right here, horizontal, is V0 cosine theta times t, if you can find the t. This guy right here is going to be V0 squared sine squared theta over 2g. This will give you the h. This will give you the range in that regard. You're going to get two times right here, guys. You're going to get a time that's very small. You know what time that is? That's right when it leaves the club. It reaches 5.5 meters in height. After a relatively long time, it also reaches 5.5 meters in height, and that is toward the end of the journey. If there was no hill there, it'd be toward the end of the journey. So that's A, B, C, guys. Here's A, here's B, here's C. Let me pick up on that right when we get back next time. And then I'll finish the last ones as well. So let's have it for the 60, the 68. We'll come right back to that. In the meantime, if you are watching this video right now, you do it. Confirm what I'm going to get. Confirm what I'm going to get for 60. We'll also do 68 and 70. All right, guys. Thank you, and we will talk to you soon.